journey of the transistor begins with John Bell, an employee of AT&T, and his patented invention, the telephone. The expiry of Bell's patent in the 1890s saw competition open up in the telephone market, leaving AT&T needing a competitive advantage. They planned to create a transcontinental telephone network which would provide instantaneous communications across America. However, phone signals at the time could not cross the distances required, as over distances they became weak, inconsistent, and unreadable. In 1906, American Lee D. Forrest developed the vacuum tube triode. This device relied upon the thermionic effect, whereby a filament heated inside a vacuum tube will emit electrons to amplify electronic signals across a circuit. This allowed signals to be sent from coast to coast, as the amplifiers were set at regular intervals across the country, and incoming signals from phones would be boosted so the outgoing signals would not lose strength. This allowed telephone calls to span large distances, provided enough vacuum tubes were in place. They could also be manipulators to act as switches by varying the resistance inside the tube, leading to their use in early logic circuits and computers. However, vacuum tubes had several limitations that prevented their use in later communications. Firstly, vacuum tubes consist of many fragile parts. The glass casings of the device were prone to breaking, and the thin filaments used for the heating element made the thermionic devices difficult to transport to regular amplification sites. The glass casing which surrounded the site also caused the device to be quite bulky. First World War II computers required 2,400 vacuum tubes, a small room's worth of space. Secondly, triodes draw huge amounts of power, particularly on startup. Large amounts of energy are required to adequately heat the filaments. Consequently, large amounts of heat are also lost to the environment. The aforementioned computers drew 15 kilowatts of continuous energy just to run a 2-bit computer. Finally, vacuum tubes were extremely unreliable, constantly needing to be replaced, as the high temperatures required for the devices limited the durability of the parts. This unreliability, coupled with transport difficulties, was a large issue with telephone networks in the 1940s and 50s. The failings of the vacuum tube led Bell Labs to research a more reliable and efficient method of amplification. Bell brought together John Bardeen, William Shockley, and Walter Brattain to engineer this solution. Shockley had been investigating the nature of electrons at the interface between metals and semiconductors for years, believing he could create a solid-state amplifier. However, he'd been unable to create a working model. Bardeen and Brattain were employed to deal with production and engineering. The pair applied two gold-foiled electrical point contacts extremely close to one another on the surface of a germanium crystal and found that the output voltage was higher than the input. Bardeen and Brattain had discovered that the electron flow through semiconductors was both possible and resulted in signal amplification when crystals were placed one next to one another. The germanium, when doped with impurities of either gallium or arsenic, would create P and N-type transistors respectively. Bardeen and Brattain dubbed this device the point-contact transistor, and soon after connected several of these transistors to other components, making an audio amplifier. This amplifier was shown to Bell's executives, who were particularly impressed that the transistor did not need time to warm up. William Shockley continued to work on the design of the point-contact transistor. He did away with troublesome, delicate point contacts, instead using both P and N-type semiconductors in the transistor and having 3 distinct terminals. This made transistors more rugged and more applicable for use in communication technologies. All 3 were awarded Nobel Prizes in physics for their researches in semiconductors and the discovery of the transistor effect. Despite Brattain and Bardeen's initial contribution, it was Shockley's junction transistor that was ultimately to be mass-produced, finding use in phones and television, as well as contributing to the founding success of Sony Electronics. Continued technological advancement has seen transistors continue to shrink in size, whilst in the mid-1960s the semiconductor material changed from germanium to silicon, increasing durability and further improving the ease with which transistors can be mass-produced. Transistors overcame 3 problems that were presented by the vacuum tube triodes. Transistors are much smaller, with up to 1 million transistors per square centimetre, allowing for more complex logic systems of computers. Transistors are more durable than vacuum tubes as they have no loose parts, and the lack of a heating element increases the lifespan of all parts. Transistors are also more efficient, drawing less power than vacuum tubes and emitting less waste heat. They also allow for an increase in speed, as transistors do not require time to heat up and can operate at higher frequencies. These improvements have caused transistors to be used in radios and phone lines to increase the range of communications, and computers built with integrated circuits, which rely upon the transistors used as a switch. Thus, the discovery of Brattain and Bardeen has led to huge advances in communication technology.